My name is Johannes Brechberger. Welcome to my talk. Welcome to my talk. I'll be talking about writing a firewall building a Lightning Fast Firewall in eBPF. And working with Linux. It's the first time that I give this talk on a Linux machine. Yeah. If anyone of GNOME is here. Yeah, okay. Anyway, that's the reason why I never do a presentation with a Linux machine. Try pressing F11. Oh good, the Linux god is here. Could just pull out my Mac. Okay. It works well. It does. Is it F11? It's so embarrassing. Is it F10? F5. Okay. We have experts in the room. Yes. Oh, you're from Connecticut, no, aren't you? Okay. Anyway, welcome to my talk. Now I've wasted 3 minutes on this, but anyway, I only have 100 slides left, so let's start, because we're lightning fast. So consider you have a simple web application like this here. It's my JFI events application on the web where you can easily see all the JFI events. And consider that now your web application is under DDoS attack. So there are a few simple ways to deal with this, and one way is the naive way. It's just by cutting a cable. So I hope I didn't cut the cord, the HDMI cable, but no, I just talked with the tech guys. Thank you. So yes, you could cut cables. Please, if you ever want to do this with plugged-in cables, don't do it. It could crash all your systems because there's impedance on it, there's power going it, and you could be not electrocuted, but your laptop could be fried. Anyway, that's the naive way, but if we don't do it this way, there's also another naive way. It's we drop the packets in our application. So when we get DDoS, we just say, oh, we're getting too many packages from this one application, from this one IP address. We just block it. It's pretty simple. We just have a hash set of blocked IP addresses. If we block an IP address, we add it, and then we can regularly ask, like, hey, is this blocked? And then we drop it. We can drop it directly in Spring Boot or something. And that's pretty decent because it works. The only problem, it's not that fast. So consider now our network stack up there. You see in the top you have our application, and that lies on top of a large Linux network stack, and then comes the network interface. So the packet comes in from below, goes all the way up, and then we drop it at the last possible location in our application. It doesn't sound like a good idea. So we use a firewall. We know how to use runtime get runtime exec. We can execute IP table commands and attach it. And it looks decent, it works, and it's like a typical solution that you do in the first try. But the only problem is it's not nice. We don't control anything. We just rely on IP tables, and it's probably not doable if we block like a couple of thousand IP addresses. So how can we improve it? So we see here that's the number of packages dropped per second. It's from Cloudflare. They did some benchmarking in 2018. They found it's pretty decent. We can they could block with a single machine. They could block like 1.6 million packages per second. And that's pretty cool with IT labels. But we want to become a 10x firewall because it's all a game of like become 10x developers with AI and everything. Now let us become a 10x firewall, because you see here the lower bar is fairly lower, the larger bar is larger, so the larger bar must be better. And what is the larger bar? If you see it maybe in the back, it's XDP, and that's like dropping packages as close as possible to the network interface. And the cool thing is we can even have hardware, we can even have offloading, so we can pull the network package dropping, the network package analysis directly into our network interface controller. So the packages never reach our CPU, and the important thing is there are allocations happening when a package enters your when your package enters your system, and then another allocation happens when it enters your network stack. And when we drop the packages further down, we prevent allocations, and thereby we have less cache misses and everything, and so that's nice. And this even sets off the cost of recomputing, of rechecking the IP address and passing the IP things here. So the traditional ways to work with this, it's pretty simple. We can either change the kernel or we can change the kernel module. Both of these options are really good. To quote Greg Hartman, you think you want a stable kernel interface, but you really do not, and you don't even know it. So we can't expect any stability there. So when we change the kernel, it's really hard. We have to convince Linus Torvalds to also agree to it, and we all know how easy it is. Or we have a kernel module, but it changes all the time. An example is the USB API, because you probably know that USB changed a little bit from USB 1.0 to like 3. Whatever we currently are, USB 4. So the interface changed quite a lot, and for this reason, we don't want to do it. And so, can we do better? Yes. And it has to do with bees, because we all like bees. It's the main pollinator, and it's the main thing that we can use for pollinating firewalls. How weird this metaphor is. eBPF is a crazy technology. It's like putting JavaScript into a Linux kernel. To quote Brendan Eck, who is famous in the internet for shouting at hard drives to show his monitoring solutions, he looks this way normally. And he's right. It's really, really cool, because eBPF is making the Linux kernel programmable at native execution speed. And that's real nice. And now, in the next couple of minutes, I tell you how it works, and then we go further onto firewall. So how it works is you take your source code, you write it in some language. I tell you a little bit more about this. Then we compile down to some kind of bytecode. It's usually more, it's not like the Java bytecode. It's not as expressive, but it's a pretty simple bytecode. And then this happens in pseudoland, and then we have to put it into the kernel, because the programs have to run in kernel. You drop packages inside the kernel. So you have a system call. For those of you who don't know Linux, system calls are like API interfaces. These are like your network APIs. It works the same way. It's like encapsulated. So the user land and the Linux kernel land are separate from each other. And then we don't want to trust that the compiler does everything right, because it sometimes doesn't, and we don't want to trust these, so we put it into a verifier. And the cool thing is, the verifier can check simple things like every out-of-bounds exceptions that we know and like in Java. Null pointer exceptions are also prevented, because it forces us to put in null checks, and also enforces termination. For all of you here with a PhD in computer science, do you see a problem with the verifier? Yeah, the one person that I know has a PhD in computer science nods. Of course, it's the theorem of Rice. It tells you that we can't prove anything in general with programs, and so we can tell you more about the science behind it later. But anyway, the idea is essentially that we impose constraints on the programs that we can write. For example, we impose constraints on the amount of steps that can be taken. So the programs are directly not Turing complete, but they can be with some tricks. So we can prove termination and a whole lot of things. So it makes it safer. But importantly, it doesn't tell you that the program doesn't do any malicious things. I can show you later how to do some malicious things. Anyway, we then take the program after it's accepted by a verifier. It's cool. If not, it emits you a random error message with some assembly in it that it's really nice to read and to debug. Anyway, then it goes into a JIT compiler. We have JIT compilers here for all the major platforms, for x86, ARM, PowerPC, and even like S390 for all those EPM folks out there. And what we can do then, we can attach these programs that we developed onto things like our network interface, the sockets, the syscall. And that's pretty cool, because we essentially can extend it. It feels more like these hooks that you have in frameworks. And it's cool. This can then use syscalls to communicate back and forth. So the cool thing is here, the eBPF runtime gives safety and security, because we have to verify if we check it. It's kind of sandboxed. we have continuous delivery because we can just easily recompile a little part, attach it, and so on. Then it's efficient because with Java, we have just-in-time compiles like we have in Java, which is very nice, and it's a standard. It doesn't change, and even if it changes, there are approaches to mitigate this. So this is pretty cool, and it's one of the leading technologies in the field of software. To quote someone, when they started, I think it was Thomas Graf who said that when they had in the beginning, when they were developing this in like the 2016 or something, they were like, hey, we already have computation defined in software with like Docker. Why can't we have proper software network defined in software? And that's essentially what this is. But it grew. So I show you later some applications that are beyond my wildest dreams. And it's pretty cool, even with nice mascots. Anyway, so the problem is, of course, we have these programs in the kernel, but we want to share data. So two typical approaches to sharing data normally is as you see on the top, we send some messages around. It's pretty easy. We use sockets. The only problem is there's some overhead that we don't like, and this messaging back and forth, it's a pretty simple data structure, so we might want something more complex and also more performant. So the other thing is shared memory. That's pretty cool. To process two tasks, just access the same piece of memory, but we have like overhead, but we have to implement our synchronization ourselves, so that's not good for code that like goes into a kernel, and you don't want to have any user space code access kernel level code because this can be quite bad. What we instead do, we have syscalls that allow us to use BPF maps, and BPF maps are like the Java collection framework, just that these maps are shared between user and kernel, and then we can access them from both sides and can store data and pass data. And there are a couple of maps. There are hash maps with LOUs, with last recently used semantics, ring buffers, and more, which is pretty decent. And we use this to have stateful applications because network interfaces, the firewall needs to have some state at least. And we can also use it to configure this. So for example, for the firewall, we want to configure the set of IP addresses or the set of rules for blocking or for letting things pass. And we can also do some basic logging. And as I said, we have a couple of eBPF maps. The list is ever growing because someone needs something and they just implement it and now it's there. If you ever develop something in C when you didn't have any collection framework, it's far better because the hash maps are very nice. We have arrays. The only problem is it's all pre-allocated because we don't want to malloc all the time, and that's also not the best thing, but it's fine. And also the verifier knows about the semantics, so the verifier knows, when you get something returned from a map, this could be null because an entry, when you access an entry and it's not there, it returns null. It enforces you to check for this, and this is pretty nice. It sometimes feels even safer than writing Java code, if I'm honest, to write eBPF code. Anyway, we have lots of hooks. We can essentially hook everything because we can hook network interfaces, sockets, syscall, file descriptors, even userland code, which is pretty cool. And if you want to learn more, I have a whole list of resources at the end of the thing. The cool thing is here, you can not only use it for security and firewalls and such, you can also use it for profiling. So if you ask every one of your profiling vendors or observability tool vendors, they use it under the hood. And you can also do it to use it for security modules. For security control, because you remember this, there's like a thing in a picture from the Zurich airport. It was CrowdStrike and it was caused by someone, by I think an array out of bounds access or something. The verifier prevents it, and that's pretty cool. So yay! And the verifier is also cool because I myself, I come a little bit from the field of program verification and program analysis, and that's a win. So you have a program analysis tool inside the kernel, and they put so much effort in, but of course it has bugs. So every one of your software, when you're developing software, has bugs. This has too, not that many, but still. So don't run eBPF code that you get from the internet, only run it from trusted sources. Because in the end, they have kernel access. They can do everything. They can access every piece of memory, which you probably don't want. Else you might be a scam vendor. Maybe you. Anyway, next career opportunities. The eBPF ecosystem is quite nice. So we have on top, we have the, as we said, we have the networking, security, and everything. Here vendors that applies. They build on top of other tools, and also there's frameworks like Catron, like load balancer and everything. And then below is like the SDKs that you can use for develop this. There's SDK for Go, for Rust, for C, everything. And then on the bottom is the kernel runtime. Anyone see something missing? Yes, just shout in. What's missing here in the SDKs? Yes, Java. Yeah, that's also what I thought like a year ago. And I thought like, it can't be that hard. Because eBPF is a great technology. It's like putting Java into a Linux kernel, or to quote one of my most favorite contrast trails. I want to use a programming language which doesn't only run in user space. And that's why I come here. That's hello-ebpf. It's my prototypical library to use to be able to write eBPF programs in Java. It's a prototype. The link is up there. You can try to use it, and it's pretty fun to play around with it because it essentially allows me to integrate eBPF applications directly in Java applications. So now is the part where I'm like live coding, or how I call it, having fun with eBPF. So what I show you first is a small demo, just that you see that they really implemented a firewall in Java and eBPF. So good. So what I did here, can you all see it now? Cool. I hope I can start it now. So I just started with firewall Spring. Cool. That just starts the Spring application, and then I can load it. So essentially, you have here an interface. It's not developed by me. That was ChatGPT who did it, because I'm an OpenJK developer. If you haven't noticed, I work at Submachine, I work at SAP. We're like one of the biggest contributors to this whole OpenJK field, so yay. And we're also big in the clip space, someone told me. So the cool thing is we can directly integrate into Spring. So assume we're now sending rule out. The rule is essentially block everything with the source port 443. So block every HTTPS connection so we can send it. And it's directly like transferred into a Spring Boot application and then directly pushed into the eBPF maps. And what we could do is just request google.com. And you see here, the package was blocked. And that's all done with the magic of eBPF. And then we can also reset the rules, and we see that it should work again. And that's pretty cool. And if you look at the code, it's not that difficult to understand, because what we're essentially doing when we add a rule, we just put it into these eBPF maps, and I'll show you in a minute how they work. And that's pretty cool because we directly push it into the kernel. So to start with a sample, to start with a sample here, we want to do something pretty simple. We want to write a simple firewall that just blocks every third package or something. So what we can do is we just, here we are in IDE, in IntelliJ. Oh, yes. How do I go in presentation mode? Thank you. Thank you for the presentation mode. Enter presentation mode. Cool, thank you. So is it now readable for you? Good. So essentially, it's pretty simple. We just told, hey, eBPF, and also usually we want to license JPLB2 because then we have access to more innards of the Linux kernel. What we then want to do is just simple implement something. So we extend the BPF program. This offers as some utility methods for loading the BPF program. Then we implement it, and for example, XDP hook. Then we just implement the XDP hook. It's pretty simple. It's a Java interface. You can see it here. It's nothing fancy. It even has documentation. And so what we can then do, we probably want to have a global variable with the count. And what Java doesn't have is unsigned. So we have an annotation unsigned because the EPF ithroat has unsigned. So we define a global variable. That's not hard. And oh, yes, that hopefully changed it. We can put in int, and then we can just implement a simple function in BPF that runs in kernel space. That's probably the important thing. So we can have public boolean should I think it was should drop, and what should drop does is pretty simple. Counter dot get modulo 3 is 1 in every third packet, so it's dropped. And now we have execute, so we can do something with it. And so what we can do, there are a few methods there that we can use. And for example, one of them is handle packet. So let's see. You can just implement, and handle packet is this method is called by the kernel. Is called by the kernel every time when we get a packet in. Pretty simple. So what we can do, we just count, we increment the counter, and then and then it's a simple enum here. That's a simple enum that we emit. You probably see it here. It's just an enum that's like aborted or something. So yeah. So that's essentially all. That's all. We only have to write a main method because we're in Java. So what we do, we create our program. Sorry, we load our program here, and then attach XCP. And yeah, that's all. And then I don't know, system.read is always nice because just system.in.read just stops and throws IO exception. That's nice. The only problem is we don't get any like feedback where the pictures are really dropped. So what I usually would do is I would put in a I would just write something out, BPF print. So we can just print F. So or like I don't know, just hello world here. And the cool thing is this code here, the code in the main method, this runs in this all above runs in the kernel, so it runs on in your Linux kernel, and this just runs locally. So let me exit the presentation mode again to have the pictures here. So what we can do, it's pretty simple. We have to compile our whole application. And while this is happening, I'll tell you about how it works. So show you in a minute how it works. Essentially, we're transforming this code into C. So it's well known that you can take Java code and create C out of it. And I'm not the first one to do this, and I'm also not the first one to get errors. Oh yeah, that happens to me in every presentation because it has to be filed. So essentially, I model C code in Java here, and the cool thing is this part is really running in the kernel, and this part is not running on the kernel, it's running locally. So you can easily integrate it, and that's how my firewall and string essentially worked. We can do more things. I have more interfaces. For system hooks, for system calls, I have a hook interface where you can hook every time you enter you enter a system call and more. And yeah, now we can run it and see where that works. yeah, you see we're plugging a lot of packages. We're plugging every third package, and yeah, don't admit when I'm plugging them, but you see here that the Wi-Fi is pretty often active. I don't know what it's doing, but maybe, I don't know. But yeah, that's what we do. And the cool thing is that works. You can just try it out. You're Maven package call away from writing your own kernel code, and you probably all wonder how it works and how it works. And then the hood is essentially the package comes in from the internet into your network driver. The network driver calls the eBPF program that you saw that we written in Java, but it works internally. It says yes, no, parses it to the network stuff. If it parses, this gets sent back to the application. It's probably Firefox or Chromium that's running. It's requesting this. And then your eBPF program we can access the counter from the Java program going down and asking getting the information from the kernel code, but also the other way around when we set values. For example, we could set the blocked IP addresses, and that's pretty cool because we essentially write Java code in the kernel. To quote Clark's second law, the only way of discovering limits of the possible is to venture a little bit past into the impossible, and that's what I did when I started in August to write this, because I think it allows us to write our applications directly in Java without having to switch languages. And it's of course based on Panama, so this is what's used with our interface to interface with this. But how this essentially works is we take our Java code that you've seen, that we've written. I then take an annotation processor here that essentially preprocesses this, and then it emits some C code, and I'm doing this on a syntactic level, but it's pretty easy to comprehend. It's not large, and then in the end we use a C compiler to compile this to eBPF bytecode. And the first time I'm doing this in public, so I hope it worked. You might have seen some stutter in the first part of the conference. It was because the scheduler that was running in the first part of my talk was actually a demo. So it's not hard to write schedulers. Ta-da! So that was my initial thought. Hey, how hard could it be? 1 year later, it's hard. But so to write your own scheduler, it's not hard. And I'm entering presentation mode again. It's not hard, essentially. You implement the interface scheduler. How hard could it be? You then initialize the scheduling queue, and every time a process comes in, you enqueue it, then give it a time slice. And then every time a CPU is hey, I want to consume something, you tell it, hey, consume from the scheduling queue, and that's all. You attach the scheduler, and then you've written a functional, not that performant, not that really good, but usable Linux scheduler in less than 40 lines of Java code if we ignore the imports and everything on top, and that's the culmination of my work here. And it was a weird journey when I started. I never knew that I would drop in and be oh, in the end I contribute to kernel code. But yes, you can now write kernel code like schedulers in Java. So why not? Why stop there? World domination for Java. Maybe there's other frontiers where we can use Java, and that's really what I like, is to show the impossible. To show people, yes, Java might be as close to my age as I want to admit, but it's still cool. It's driving, and I think pushing the environment, pushing the ecosystem forward is also what we're all here, and that's why I like the community. So my idea is, as a glimpse into the future, to use Java as a first-class language for eBPF, use it in a place for education, because many people know Java, and I can teach them eBPF by using Java. And it's also moving all in all towards a microkernel, making it possible to implement more and more stuff in code that we develop ourselves and that doesn't come from the Linux kernel. We can use it to fix and probably not in Java because it's more like for educational purpose, but maybe let's see what the future brings. And as I said, you can write schedulers in Java, and it uses under the hood the scatxt. That's the Sexopus on top. It's official new logo. I think you're one of the first people to see it. It's was just created, and it's the idea that you can write schedulers in eBPF, which is pretty nice. And I think with a couple of minutes to spare, that was my talk. If you want to read more, I have lots of resources, too many to count on there. I also write a blog. I write blog posts every 2 weeks on everything Java related, because in my day-to-day job, I'm essentially working on creating a new CPU time profiler for Java. So it might be hitting Java 24, Java 25, JK24, JK24, 25. I'm Johannes Bechbe. You find my blog there, or mostly Nerd.de, or on Mastodon or Twitter somewhere. I want to say thanks to Tilda and Rama Inc., who helped with this project, and also my team who allowed me to spend a few Friday evenings on this. And if you want to know more about Submachine, we're really cool. Just come later to me. I even have stickers with this nice logo. So yeah, thank you for being here, and have a nice time at the last day of the conference. And thank you. I think we probably have time for some questions because I finished early. So, and please don't ask the question why, because when we was at Linux Plumbers conference, one of the questions was why I thought it was a joke. I was at a Linux kernel conference in Vienna. So any other questions besides why? Yes. So the question was, how do you notice when you do something stupid? The thing is, it's with all your applications. When you do something stupid in your Java application, how do you notice this? By testing, by stress testing. So it's like when I develop normal applications like my profile stuff, and I put a while loop in there and it doesn't finish. Nah. The cool thing, the verify prevents you from from many of the stupid stuff. But yes, just test it, just benchmark it. It's skill you learn, and I think we're all here seasoned software developers, at least you are hopefully, and testing, performance testing, yeah. I think there's projects related to profiling in PF programs, so there are people out there. The question is where you can crash the kernel. I think probably the verifier prevents you from most of the terribly stupid stuff. So accessing memory that you shouldn't have access to. But of course, you can probably crash the kernel with it, especially because there might be still bugs in. So as I said, don't get it from untrusted sources. Run it first on local devices. Run it only in production if you're really, really, really sure. And don't run it in production when you're just a Java developer, discover hello-ebpf and be like, oh, I write something and then I push it to 1,000 servers. Don't. But it's the same thing when you start out developing and you push a fix to your library, and now everything crashes. So as I said, it's just normal software development. You can do it in your IDE. So yeah. Oh yes, of course you need root privileges. It would be pretty horrible if you wouldn't. So yes, the idea is you have root privileges, you need them, and that's a really good thing. And there's a specific capability. I think usually it's enabled with root, but there's also a specific capability related to BPF. So yes, but normally you get it. So you can configure it, and there are approaches to more restrictions. But yeah. Yes.
On your every third package example, the methods you put into the BPF are automatically atomic, right?
You found a good you found something good. Yes. Oh no, they aren't. So where are we? We are in a sample. So you found a backend. That's nice. That's just a simplification. So one thing is we could use atomic theory. So we could use an atomic set. I don't think that I implemented atomic centers, but essentially there are atomic functions that you can use. It's also exposed to hello-ebpf, and they are not in itself atomic, just because this would cause such a large overhead. But for example, here in this example, you could essentially assume when you have one network interface and you attach it to one single interface, so that it's essentially sequential, so you don't have issues because the network interface receives them one after another. Otherwise, this TCP/IP stack would be what? So in this case, you probably don't have any issues. But of course, when you have more complex data structures, you get to these problems. I think many of the maps should be thread safe. Just look into the documentation. It's with every project. Getting a thread safe is hard. The cool thing with firewalls is that it's pretty decent when you have one network interface. It's essentially sequential, so it's the easiest way. What we can also do, so consider we have a system call hook. Let's see whether it works. Okay, I'd override. Good. I hope. So what we can also do, we can take a look and search for something like open2. That's a method that's called whenever. Usually when files are opened, then you have a problem because you can open files from different processes, and then you would need to see that, okay, counter, when we update it, it's not in itself atomic. Well, of course, we could assume when we're running on an x86 machine that it might probably be atomic enough for application, and so it's difficult. And that's the part when you add this part of the reasoning, I think you already fell deep enough into the rabbit hole that you can fall a few steps later and create a rabbit for me and Alice too when she's still there. Anyway, I think we have a few more minutes for questions. Any more? Yes. Yes. Of course I use the FFM API. So the idea is we can even see it. So the BPF program. So let's see how it loads. Let's see. I think I have the XDP attach. So that's how XDP attach works. It just used this is auto-generated by the code generator that's with OpenJDK, and I then just used the FFI API. Without the FFI API, it would be so much worse. It would be so much effort down. The FFI API was preview in 21 and now stable since 22. Is such a godsend. Makes it so much easier to write things, which I wouldn't have done before. I wouldn't have done this project without it, because I essentially all the calls I do in Java and userland are directly to Java. The only thing is directly by FFI. The only thing is, of course, what I have to do is I had to implement all. When you see that I have like data structures, you saw probably that we have when you're going back to the firewall example, that we have in the firewall example some rules. We have some structs there, some types there, some enums there. I wrote the code that maps this to the native memory, that parses native memory to this and maps it back in. So there's a whole serialization library with things like auto layouting structs, so have the same layout as the C compiler baked into this. If you're interested in this, just read into my blog. So there you can find an explanation of through how many hoops I jumped. I think probably we have room for one more question. Is there any? Otherwise, I'm here for the rest of the conference. Good then. It was nice speaking with you. It's the first time I gave a presentation on this laptop with a scheduler that I wrote in Java running live, and it didn't crash, which I will like. So have a nice OCX conference then, and have a nice day.